Torque and moment of inertia. Remember Newton's laws of motion. In linear motion, we said the first law of motion is when an object at rest remains at rest, an object in motion remains in motion unless there's an outside force acting on it. For torques, it's the same thing. An object will rotate and continue to rotate, or an object will stay at rest but continue to stay at rest unless an outside torque acts upon it in a rotational motion. So the first law of motion, or the law of inertia, tells us that objects have a resistance to motion. And that is what moment of inertia is. It is the object's resistance to rotate. And we label moment of inertia with a capital I. In the second law of motion, in linear motion, we said that F is equal to ma. When we do force in a circular motion, that is torque. And torque is equal to force perpendicular to the lever arm, or since it causes objects to rotate, it is equal to I, moment of inertia, times the angular acceleration. So in the previous units, when we had a pulley with a mass, we ignored the pulley because the pulley was massless. But when we talk about moment of inertia, we must include the pulley. So the first thing you're going to do is you're going to draw a free body diagram. Since there are two objects, you are going to draw two separate free body diagrams. One for the pulley, which has the radius of r and a mass m, and a free body diagram for the hanging mass m1. Body diagram for the hanging mass. We know it has a weight, Fg1, and then it has a tension going up due to the rope. Since this weight is pulling it down, when I write my Fy equation, the direction I'm moving, I'm going to make positive because this will cause less math errors. And so we have Fgy, because the direction is going down, minus T is equal to M1A. So that is the free body diagram for the M1 as well as the equation. So for the pulley, we have the weight of the pulley. We also have the tension or the force from the string that's going to produce the torque. And then we have a normal force from the pivot point. So if I write my torque equation, and I have to write a torque equation here because the pulley is rotating, torque we know is equal to force perpendicular to the radius from the pivot point. This is also equal to the moment of inertia times alpha. So what is the force producing the torque? The force that is producing the torque is the tension of the rope. So this tension here and this tension are exactly the same. So I need to solve my Fy equation for T. So if I do that, that's Fg1 minus M1A. So if I plug that in, that's going to be Fg1 minus M1A times R. R is the radius of the pulley. Remember, torque has to be perpendicular to the force. The force here is the T, the tension of the rope, times the radius. This is equal to I, the moment of inertia times the angular acceleration. We also learned that we could substitute in for angular acceleration because acceleration tangential is equal to r, the radius, times the angular acceleration. So angular acceleration becomes a tangential over r. And so if I substitute that in, that becomes Fg1 minus m1a times r is equal to I at over r. And the tangential acceleration is the same for the mass here and the pulley because they are tied together by one rope. So solving for I, we divide both sides by at over r. So this becomes Fg1 minus m1a times r divided by at, and since there's two r's, it becomes a r squared. So again, to solve these problems, if there are 3 or 4 objects, you draw a free body diagram for each one. If it has a rotational motion, you write a torque equation. And the torque is going to be force times r equals to I, moment of inertia, times the angular motion, angular acceleration. Remember, the acceleration, the tangential acceleration, is the same for the whole system because they are bounded by one rope. We do not include the normal or the weight of the pulley as a force in our net force because they are at the pivot point. So R is 0. Next, if you notice, for FR, we made F positive. Alpha is positive because the direction the pulley was going was down. We made that the positive direction, therefore alpha is also positive. If you choose to make F negative, then you have to put a negative in front of alpha. So the direction you move, always make positive. And afterwards, you just plug in. If they give you I for the pulley, which is 1/2 mr squared, you could plug in and solve for a tangential. Pause the video, derive the tension and acceleration equations, and check your answer. We're going to assume that the pulley is going clockwise because M2 is lower than M1. Since there are 3 objects, we must draw 3 free body diagram. So for M1, we have weight 1, and then we have tension 1. For object 2, we have weight 2, tension 2. When there was no rotational motion and the pulley was massless, the tension in the rope were exactly the same. But when there's rotational motion involved, T1 and T2 may be same, may not be the same because they produce a torque. So we need to solve for T1 and we need to solve for T2 by writing a general equation. So the sum of F1 is going to be T1 minus Fg1 equals to M1A. Since T2 is going up, T1 has to be positive, M1A is positive. And remember, the entire system has the same tangential acceleration. F2y, since it's going down, my FG2 is going to be positive minus T2 equals to M2A. And again, tangential acceleration is the same. Now we need to draw the free body diagram for the pulley. We know we have a T1 and we have a T2. We know that we have a CM and then we have a normal. We know the normal and the weight of the pulley will have no effect in the torque because it is at the pivot point. So my general formula for the torque is going to be F net R equals to I alpha. We're going to assume that I of the pulley is 1/2 mr squared. We also know that A tangential is going to be R times alpha angular acceleration. Now I'm going to plug in for F net. Since T2 is moving down, or mass 2 is going down, the F net, I'm going to make the positive direction going down. So this is going to be T2 minus T1 times R. This is equal to I alpha. T1, if I solve this, is going to be M1A plus FG1. T2 is going to be FG2 minus M2A. So this becomes FG2 minus M2A minus M1A minus FG1 times R. R is the radius of the pulley, and remember the torques have to be perpendicular to it. This is equal to 1/2 mass of the pulley, R squared. I'm going to plug in for alpha since we're solving for tangential acceleration. So if I plug that in, that becomes AT over R. All the radiuses are the same, so the R down here will cancel out with the R here. This R will cancel out with the R here. So now I'm going to move all the accelerations to one side because remember, they are moving together as one, so the tangential acceleration is the same. So this becomes FG2 minus FG1 is equal to 1/2 ma. My tangential acceleration is a plus m2a plus m1a. I need to factor out an a and then divide everything by the masses. So a is going to equal to m2 minus m1 because weight is mass times gravity. Pull out a g, divide by 1/2 of m, that is my pulley, plus m2 plus m1. This is my tangential acceleration. So to find my tension, if I have to plug that in, T1 is going to be m1 times m2 minus m1 over 1/2 m plus m2 plus m1 . This is going to be plus mg1g. There's a g here. So technically I could factor one out. So this will be m1g. m1 or m2 minus m1, 1/2 m plus m2 plus m1 plus 1. And you can repeat the procedure for the second one, T2. So T2 will become m2g minus m2. And if you notice, I'm going to factor out a g here. So this is going to be m2 minus m1, 1/2 m1 plus m2 plus m1 parentheses. And if I factor m2g out, this is going to be 1 minus m2 minus m1 over 1/2 m plus m2 plus m1. Again, draw your free body diagram, write your Fy equations or Fx equation, the direction you move in, make positive, and solve. Remember, the normal and the weight of the pulley has no effect because it's located at the pivot point. And then A tangential is the same for all of them because they are moving as one. Pause the video, derive for tangential acceleration, and check your answer. So if I look at this one, again, there are 3 objects. Since friction is not present, for M1, I'm going to have weight, which is Fg1, normal, and then I'm going to have tension 1. For the second one, I'm going to have weight of 2 and then tension 2. Again, if the pulley was massless, the tensions would be the same, but they're not because these tensions will produce a torque. So for the pulley, I have a tension going this way, which is T1. I have another tension going down, which is T2. We're going to assume the object is going to accelerate downward. For my block, I only need my X equation because I have no friction present and the normal and the weight does not produce a torque. So this is T1, M1A. And the second one is going to be in the Y direction. Since it's going down, it's going to be Fg2 minus T2 equals M2A. For my pulley, I have T1, T2. I know I'm going to have a weight of the pulley, and then I'm going to have the normal, and the normal is going to go northeast to balance all my forces. T1 that is going to the west, and T2 which is going south, as well as the weight. If not, the pulley will break. Since the pulley produces a rotational motion, I need to write a torque equation. And since the object is going down, it's going to be the torque of 2 minus the torque of 1, which is equal to I alpha. Or since the radius is the same, we could write this as T2 minus T1 times R is equal to I alpha. So T2, if I rearrange this, is going to be Fg2 minus M2A. We know from the previous problem, I is equal to 1/2 mr squared for the pulley. We also know alpha is equal to AT over R, because A tangential is equal to radius times the angular acceleration. Now I'm going to plug in for my equations. So if I plug in for T2, this is FG2 minus M2A minus M1A times R, because the radius is the same, 1/2 M R squared AT over R. The R's cancel out. This R will cancel out one of the R's. This R will cancel out with this. I'm going to put all the accelerations on one side. So AT is going to equal to M2G over 1/2 the Poli's mass plus M2 plus M1. So if I want to find the tension of T1 is M1A. So I plug that in. This is M1 M2G over 1/2 M the pulley plus M2 plus M1. To solve for T2, this is going to be M2G minus M2 times M2G over 1/2 M plus M2 plus M1, and I could factor out a Mg2. So this is 1 minus M2 over 1/2 M the pulley, M2 plus M1. Pause the video and see if you can solve this problem on your own. We have a pulley that is pulling up a mass of 451 freight. So it's rotating in this direction. This is a dual pulley. A dual pulley means there is a bigger pulley, and within the bigger pulley there's a smaller pulley. The radius given is 0.6 for the bigger one and 0.2 for the smaller one. The I is given for the dual pulley, and the tension of the motor is 2150 newtons. They want you to find the angular acceleration. So pause the video, solve it, and check your answer. I'm going to draw 3 free body diagrams. So we have the motor. The motor has a weight, and then it has a normal, and then it has a force, and we know what this T is. We don't care about the normal or the weight of the motor because it is located at the pivot point. Then we have the dual pulley. The bigger pulley, we have the tension. This is the tension of the motor. We have the smaller pulley, which has the weight tension. This is the tension of the crate. We also have a normal, which is something like this at an angle. And then we have the weight of the pulley. And again, we could ignore the weight of the pulley and the normal because it's at the pivot point. Now we have the crate. The crate, we have a weight. And then we have a tension of from the rope for the cable or the crate. So now I'm going to write my equation. My crate equation is going to be sum of Fy. It's going to be Tc minus Fgc equals to Mca. The reason is TC is because the crate is being pulled up by the motor. My pulley equation, you know it's going to be a torque equation. There are only two torques present. Now I'm going to write the torque equation for the dual pulley. So the torque is going to be the torque of the motor minus the torque of the crate. This is equal to I alpha. We don't need to substitute in for I because they gave you I as a value. But we also know A tangential is equal to R alpha. The reason torque motor and torque crate are separated is because the crate is on the smaller of the dual pulley, so the radius is different than the torque of the motor, which is on the larger part of the dual pulley. Also, the torque motor is positive because it is being pulled towards the motor. And remember, the direction you move, you want to make positive because then you don't have to correct for alpha on the other side. So if I substitute in equation values, this is torque motor becomes tension motor over R of the bigger pulley minus, this will be the tension of the crate, which is equal to MCA plus FGC. So this becomes MCA plus FGC times the radius of the smaller one. So I'm just going to put that as crate. This is equal to I alpha. Since the pulleys are put together, it's a dual pulley on the same axle, they're going to have the same angular acceleration. So now I'm going to substitute in for the tangential acceleration of the crate because since they are on the same dual pulley on the same axle, they're going to rotate at the same angular acceleration. This becomes T motor, R motor minus MC, so A tangential, this is A tangential, becomes R C alpha plus FGC RC is equal to I alpha. So now I'm going to put all the alphas to one side. So when I do that, this becomes MC RC alpha times RC. So I take this component and multiply by RC. And I moved it to the other side, so that becomes plus I alpha. And on the other side, we're going to have this minus FGCRC. Now I'm going to solve for alpha by taking out alpha. So this becomes TM RM minus FGC is just the mass of the crate times gravity times RC divided by MC. This is going to be RC squared plus I. So now I'm going to substitute in. The motor was 2150 newtons. The bigger pulley had a radius of 0.600 meters minus the crate, which was 451 kilograms times 9.8 meters per second squared times the radius of the smaller pulley, which is 0.200 meters, divided by the crate's mass times the radius squared plus the I that was given, which is 46.0 kilograms meters squared, becomes 6.339 radians per second squared. To find the tension on the cable, start with the torque equation. Torque motor minus torque of the cable equals to moment of inertia times angular acceleration. So torque cable becomes torque motor minus I alpha. If I substitute this in, this is tension times R. This is tension of the motor times R of the motor minus I alpha. So TC becomes TM, RM of the motor minus I alpha times RC, which is 2150 newtons times 0.600 meters minus the angular momentum, which was given as 46.01 kilograms per meter squared, times my angular, which is 3.4 radians per second squared, divided by RR of the smaller pulley, which is 0.200 meters, which gives us approximately 4,902 newtons. So draw your free body diagram for every object. Anything that's rotating will have a torque equation. Anything that is not rotating, you will write a sum of fx or a sum of fy and substitute in.